Good morning, everyone. Today I'll be presenting an overview of breadth first search algorithm, commonly known as BFS. In this presentation, we'll explore how BFS works, its applications, and why it's a key algorithm in graph theory and computer science. So, coming to presentation outline, let's begin with a brief outline of our presentation. I will start by introducing BFS and describing the problems it solves. Then we'll examine several real-world applications of BFS. Next, I'll walk you through the step-by-step operations of the algorithm. And we'll work through a small example to see it in action. We'll then analyze its performance, and finally, I'll conclude with a summary of the key points. Coming to problem description, a BFS is a graph traversal algorithm that keeps, explores nodes in a level by level manner. This makes it particularly effective for finding the shortest paths in unweighted graphs, where every edge has the same cost. Additionally, BFS is used to check graph connectivity and even detect cycles in certain cases. Coming to applications of BFS, BFS has many practical applications. It's used to find the shortest path in unweighted graphs, a common problem in networking and route planning. Web crawlers use BFS to systematically explore and index web pages. In social networks, BFS helps in suggesting friend recommendations by finding connections between people. It is also employed in broadcasting algorithms in computer network and even in AI for solving puzzles. Coming to step-by-step operations, let's break down the algorithm step by step. First, we initialize a queue and mark our starting node as listed. We then enqueue the starting node. Next, while the queue is not empty, we dequeue the front node and process it, for example, by printing or recording it. For every adjacent node that has not been visited, we mark it as visited and enqueue it. This process ensures that we explore nodes in the order of the distance from the starting point. So let me give you an example. So consider a simple graph where node A is connected to B and B connects to D and C connects to E and F. Starting at node A, BFS first visits A, then it visits B and C, which are the nodes directly connected to A. Finally, it visits D, E, and F, which are the nodes at the next level. This order A, then B and C, followed by D, E, and F, illustrates the level by level exploration characteristics by BFS. So, performance analysis. Analyzing the performance of BFS, we find that its time complexity is O into V plus E, where V represents the number of vertices and E the number of edges in the graph. The space complexity is O into V, because in the worst case scenario, the queue might hold a significant portion of the vertices. This efficiency makes BFS especially suitable for problems involving shortest paths in unweighted graphs. Let me come to the conclusion. In conclusion, BFS is a fundamental and efficient algorithm for traversing graphs. Its level by level approach makes it ideal for finding the shortest paths and has wide ranging applications from web crawling and networking to social networks and AI puzzles. Mastering BFS is not only important for academic purpose but also has practical implications in solving real world problems. Thank you for your attention. Thank you for the opportunity. I hope this presentation has given you a clear understanding of how BFS works and its many applications. I'm happy now to answer any questions you might have. Thank you.